pleasure to have Mikel Arruabarrena visiting us from Spain. He's going to be around this week and hopes to meet other people in the department. So I'll coordinate a visit with him, and you just send me an email if you want to meet with him. I'll also reach out to a few of you to meet with Mikel. He's an expert in first principles studies of magnetic systems, and he'll be telling us a little bit about some of that work. So, Mikel, thanks so much for visiting. We look forward to your talk.
Thanks, Greg, for the nice introduction. Well, my name is Mikel Arruabarrena. I come from Centro de Física de Materiales in San Sebastian, and today I will be presenting this work entitled Magnetic Properties of Layered Ilmenite and Two-Dimensional Ilmenenes. This is a work that has been done in collaboration with several people. For example, my former groupmate Rodrigo Aguilera del Toro, Aritz Leonardo, Martin Rodriguez Vega from University of Texas at Austin, Greg, which is here present, and also Andres Ayuela, which is also visiting Boston with me these days. So well, let's see if the slide transitions. Sorry, Greg, to slide. Okay, yeah, it seems that now works. Okay, as I said, we come from the group of electronic excitations in surfaces and nanostructures in the Centro de Física de Materiales, Material Physics Center in San Sebastian, a beautiful city in the north of Spain. This is a mixed center between the Spanish Research Council and the University of the Basque Country, and it's directed by Andres Ayuela, which is with me here today. Well, moving to the talk, today, as I said, I will talk about the magnetic properties of ilmenite-like systems. And well, I'm going to present two different researches that we have been doing in the last years, that even though they are two separate researches, they are quite entangled one with the other because of the focus of both of the papers, which include ilmenite-like systems. First of all, we will focus on the magnetic properties of bulk cobalt titanate, which has an ilmenite-like structure. It's a, well, it also, even though it's bulk, has a layered structure, which brings us to our next topic, which is the study of the magnetic properties of two-dimensional transition metal ilmenines, which are, ilmenines are the two-dimensional exfoliation of, for example, ilmenite ores. We'll move to the, okay, we'll move to the first paper, which focuses on the bulk layered CTO or cobalt titanate ilmenite. This is a paper in which we did an ab initio or first principle study of the magnetic properties of this compound, and we focused on magnetic properties as well as anisotropy. Well, cobalt titanate is a material that has attracted quite a lot of interest in the last years, mainly because it hosts direct magnons in its honeycomb-like cobalt layer, and therefore it's seen as a promising material for example, spintronic applications. And there has been quite a few papers on this one with in elastic and neutron scattering experiments, as well as some model Hamiltonians to describe these magnons. And therefore, the interest in this material is high. But we have realized that even though there was a high interest in these magnons, there was not much first principle study of the fundamental magnetism or the basic magnetic couplings of this compound in this DFT or first principle framework. So that's where our work comes. Well, to present a little bit the compound, I was talking about it. It's a layered compound. Ilmenite CTO has an hexagonal crystalline structure, which is organized in by planes, titanium and cobalt planes, ordered in the hexagonal z-axis. They form octaedra, side-sharing octaedra between them. And if we take a look at it, well, you can see that even though if it's bulk, it has a very defined layered structure. And if we take a top look at it from the 0001 plane, we see how these cobalt atoms form a honeycomb, graphene-like sublattice, to say it in some way, which is the origin of having the water. Thank you. This the topological or Dirac-like magnons. So once that we have seen a little bit the structure, let's move to the magnetism. And well, in order to study the magnetism, first of all, the first thing we had to do was to take into account a proper magnetic cell, let's say, because if we just took the basic chemical cell, some magnetic configurations, such as the experimentally observed ground state, GFM, were not accessible. So we had to use a larger unit cell to include all this up, down structure. We will look at it in a moment. So how do we study the magnetism of these compounds via DFT? We do this in the following way. We mix DFT, we use DFT calculations, as well as some model Hamiltonians, which let us describe the magnetic couplings of the system in a quite simple way. Let's think about it. Here, you can see how this compound, well, we studied several magnetic configurations, but we reduced the fundamental magnetism of this compound to the presence of two magnetic couplings, J1 interlayer magnetic coupling and the J2 in-layer magnetic coupling. By means of DFT calculations, we can compute the total energy of each one of the different magnetic configurations we have, which are the experimentally observed ground state, the GAFM. It's a configuration that consists of ferromagnetic cobalt planes that are antiferromagnetically coupled in the z-axis. Then we also consider the ferromagnetic case in which all the spins in the system are aligned, and one so-called fully antiferromagnetic case in which inside the layer, the cobalt layer, we also have antiferromagnetism. By means of this model, well, this case Hamiltonians, and the total energies we extract from DFT, we are able to calculate these magnetic couplings and relate it to these energy differences. Well, I forgot to tell, but what we do all of this by using not just plain DFT, but DFT plus U, or also so-called the Hubbard-corrected DFT, in which the Hubbard-U interaction is taken into account to correct the delocalization of transition metal 3D orbitals that often happens in these kind of systems. Here we used these values for cobalt and titanate. They are reasonable values, and well, even though I'm not going to show how we got there, these values were obtained after studying a wide variety of values and by analyzing the structure, the electronic structure, band gap, so that they gave a reasonable description of the material, not only magnetically, but also electronically. So they are quite reasonable values. What we found when studying the magnetism of this compound via the J1 and the J2 constants was the following. We were able to do some kind of phase transition diagram in which we observed that the ground state was effectively the experimentally observed GAFM state with ferromagnetic cobalt planes that are antiferromagnetically coupled in the z-axis. But then we also observed that the intralayer coupling was larger than the interlayer coupling. What does this mean? That it's easier to break the interlayer magnetic order than the intralayer one. So this means that we will have two critical temperatures. At first, low temperature, we will be in the GFM state. At the nil temperature, we will break this interlayer ordering so that we no longer are in this state, but in plane, we will still have presence of ferromagnetic planes, even at temperatures that are higher than the nil temperature. So therefore, we can tell that there are two critical temperatures in this compound, and that even above nil temperature, there might be some magnetic properties in the layers of cobalt, which would be of interest in 2 dimensions, for example. If we move on, we also have to consider not just the ground magnetic configuration, also the anisotropy energy in this compound, because when we couple the spin magnetic moment to the crystal lattice, there's I'm sorry, I will define it in another way. The magnetic anisotropy is defined as the energy difference between having the spin in two different orientations. It's composed of two main terms, which we can take a look here, are the MCA, or the magnetocrystalline anisotropy, which is due to the spin orbit coupling, and also the magnetic dipolar interaction, which is due to the dipole-dipole interaction between two spins that can be considered as magnetic dipoles. These two magnitudes were computed in different ways. The MCA can be computed via DFT, while the dipole-dipole interaction, we had to make a code to manually compute all of these spin pair interactions. And well, what we did was calculating this anisotropy energy with respect to the theta angle. That is to say, we moved the spin from being out of plane in the hexagonal z-axis, and we moved it to the plane. What we see is, on the one hand, is the MCA term, as we move inside the plane, grows larger and larger, meaning that these anisotropic terms wants to be the spin to be out of the plane, while in the other, just the contrasting, the dipolar term did the opposite trend, like wanting to be inside of the plane. Therefore, this compound has two opposite magnetic anisotropic terms, which are quite large, and we see that somehow the MCA wins, and we have a slightly out of plane magnetic anisotropy in this compound, meaning that the spins want to be oriented out of the plane. But what's the problems? Well, experimentally, it has been observed that it's the other way around. The spins are in plane, and they have seen this by looking at the magnetization with respect of having the field out of the plane or in plane, and it's clearly in plane. So DFT is saying us that it's out of the plane. So what's the matter, and how we can explain this? So we had many discussions about this, and we finally did the following, which was analyzing the effect of doping on the system. And well, we did it in the following way, by considering two different kinds of doping. First of all, we consider oxygen vacancies with doping, which is just we would be equivalent to having some oxygen sites not filled with oxygen in the compound. This is reasonable for oxides, it happens. And also consider the opposite case, the N-doping, which would be having anti-site disorder or having some cobalt places filled by extra titania, instead of cobalt having titania. This has been also seen in older experiments of these kind of compounds. It's also reasonable to happen. What we did is just compute the anisotropy energy with respect to the variation of electrons in the unit cell that would correspond to these two different kinds of doping. And we observed two things. First of all, that the dipolar term remained almost constant, like the change was really small because it's mostly depending on the local spin density, while the MCA term dropped as we added electrons into the cell up to reaching this point in which it actually became smaller than the dipole-dipole, therefore suggesting that N-doping can effectively turn the anisotropy inside the plane. And well, this value, which it's a first approach, but this region would correspond to 0.2 electrons in the cell we did, which is 2.5% of cobalt sites being occupied by titania, which is not a large doping. So this is a reasonable hypothesis that could explain why we are seeing this in plane anisotropy in real samples instead of the out of plane suggested by DFT. So, as a summary of this part, we studied the whole fundamental magnetic properties of bulk CTO, and we found the experimentally observed GAFM ground state. We also found that anisotropy has two very large components that are competing one with each other, meaning that this compound is probably more tricky to simulate by models than what it was thought before. Also, doping can play a crucial role in this spin orientation. So, well, looking forward, it could be interesting to see more experiments with single crystals or in these compounds to see which is actually the effect of doping, or if we can play with it actually to tune the magnetic properties of this compound.
Quick question.
Yeah, sure.
So for the case where you end dope it to turn the anisotropy in,
Uh-huh.
are those numbers roughly consistent with experiment for like estimates of the doping level? You know,
The doping level of 2.5%.
Yeah, so like, so 0.2, well, okay, so I guess the question is, the magnetic anisotropy, is that dashed line there, which is around 0.2 electrons, is that consistent with what's measured in experiment?
The
For the
magnetic at
in-plane,
0.
like the
This
zero?
one.
Yeah, so right, so you go up and then you
Uh-huh.
have the horizontal dash line, right? So
Yes,
over to the
this
left.
is dipole-dipole interaction, which mostly doesn't change with doping because it's such it's mostly dependent on the local spin moments
Yes,
and how they interact with distance. So it's if you don't change the structure, it remains mostly constant.
right, I'm asking about the comparison
yeah.
against experiment. So in the material, the experiment that you referenced, do they give a quantitative estimate of the anisotropy energy so that you can compare?
I don't think so. They were quite the old experiments in which they observed doping and these ones, or are you talking about the newest paper?
Well, I think the newest one that you cited,
Okay.
so they said that they see the anisotropy in plane.
Yes.
Do they quantify it?
Oof, I cannot tell you right off the pattern now, but
Yeah, I'm just curious if
we
it's
can
in the
check
right ballpark.
out
Okay, when you include the doping in the calculation, does it give you the right ballpark for the experiment?
So that's a good question. I might have to look at it after the talk, which is the magnitude. Yeah, thanks for the question.
This anisotropy energy is in the order of being huge if you compare with normal nickel or manganese, nickel or cobalt or iron. In cobalt, nickel or iron, when we do these calculations in the order of micro.
Yeah, well, yeah,
now
here we have
anisotropy-
milli-EVs per atom, well, 0. Yeah.
Right, so
Yeah,
like the
yeah,
one on the
yes.
left,
It's like
I
10
guess the question
times.
Uh,
is whether they quantify it there.
I don't know how the units compare right now. It's a we might have to look at it to see
Okay.
if it fits the right ballpark. Yeah, thanks for the question.
There's some, I don't know if you want to check the chat quickly. It looks like the
Oh,
number
shit.
may have gone up. Maybe there's questions in the chat.
How can I check the chat
if you-
without destroying
Well,
the
if you put
connection?
the cursor on the chat, like go down to the bottom.
Yeah, here
Put the cursor on
I
the
cannot
chat,
see this.
and then it
Okay,
will expand it out. It looks like
here,
someone.
I cannot see it in my screen here. I'm like in full screen, so
Oh, I see.
I can't go to the chat part. Do you know? Do you mind?
I mean, you might.
There's
have
some
to
questions, right?
Undo the full screen and then come out. Yeah.
Okay, how do I do it? Escape, right?
Yeah, that should be.
Whoop. Yeah. No,
Then
no,
you
it does. It gets out of
If you look at it on your screen.
1
I'm not
second.
sure, but I don't remember if there were 10 comments in the chat or not.
It's the same.
Okay, that's the same. Okay, so maybe it's fine.
It's fine.
I do it
Okay,
full
let's
screen,
try
yeah.
to go view full screen. How did you do this?
That was in left.
A slideshow, right? Or something like
Yeah,
that.
it's like, yeah, exactly, that was it.
Okay. Sure. Yes, this looks great.
Okay.
Okay, so after this, we will move to the second part of the talk, which, as I said, is a separate research, but is closely related to this previous one, because now we go from bulk ilmenite-like systems to two-dimensional ilmenenes, which is a fancy name, but it's just the two-dimensional version of ilmenite. This, well, this was our work, studying the magnetic properties of the whole family of transition metal ilmenenes, but well, the motivation for this was, first of all, the synthesis or the experimental synthesis of ilmenene, which is a two-dimensional magnetic, non-van der Waals magnetic oxide, which was exfoliated from bulk naturally occurring, very common ilmenite ore mineral by Balan et al. And well, it looks like a promising compound because it's a two-dimensional material that shows magnetism, ferromagnetism. And well, it's been looked at for its potential as a photocatalyst, for example. Looking at well, the synthesis and that it has been realized experimentally, well, let's talk a bit more about this compound. Yeah, they did some transmission electron microscopy measurements where some single and two layers zones of ilmenite can be observed. And they also found that this compound exfoliates in the 0001 plane, or well, the hexagonal z-axis. Yes, so well, this compound was experimentally synthesized, so we were thinking about what about other transition metals. We have observed that the cobalt titanate, which is similar to ilmenite in structure, it's already interesting in bulk. So what's happening with the similar ilmenines in the two-dimensional regime? So we focused on the transition metals from vanadium to nickel, and we also took a look to the brass metals, hold the shell. So before anything, some computational details on this, because once again, we use the GGA plus U approach, but well, in this case, we had to look at a whole family of elements. And apart from using the U values that you see there for each of the elements, which were consistent with other U values used previously in literature for oxides, we notice here that we use a U value for oxygen, which was suggested for by literature when doing this kind of oxides, and also backed up with hybrid calculations, more sophisticated hybrid calculations. We observed that actually adding this oxygen parameter in the GGU approach helped more properly or qualitatively better describe the electronic structure of this compound. So these ones are the values we are working with. If we move to the structural properties of ilmenines, I have already told that this compound is exfoliated in the 001 direction, but well, this can be done in several ways. One might think, for example, to cut it in the titanium atoms and get this layer, or you can do it transition metal terminated. There's different ways. We analyzed many possibilities, and we ended up concluding that for most of our, for all of our compounds, the transition metal terminated stoichiometric layer was the most stable. It's the one that looks like this. And here you have the side view. And well, some things about this structure is that first, we no longer have this honeycomb transition metal layer. We have lost one of the first neighbors there. So now it's more like a triangular lattice. What more? There's also a heavy flattening of the structure. It shrinks in the Z direction, causing that now the titanium layer is flat and it's honeycomb-like. And this also seems to be a completely new material. So, well, computing this compound is crucial. Having calculations on this is crucial. So, some more works on stability. Apart from, well, structural stability can be extracted from the fact that there are phonon calculations already before us. There were phonon calculations on these compounds showing their stability, and well, the fact that iron ilmenine has been experimentally synthesized. So, and also about chemical stability, the compound having a, you cannot see the dots here, sorry about that. The compounds having a large band gap tell us about their chemical stability, and also that they are probably good photocatalysts.
Wait, how does that data show?
Yeah, sorry, this figure has been broken here. I think it's because of changing the computer. Well, here we have some larger band gap values here around, with some ilmenines having a band gap even larger than iron ilmenine, which is already suggested.
But I guess what about the band gap tells you that they're good photocatalysts? Like, how is that related?
Well, I'm myself no expert in the field of photocatalysis, but they are interested in, they were using the iron ilmenine on top of titania arrays, I believe, and this value of the gap around 3 was interesting in Tetragard, I believe. So I'm sorry. I'm afraid I cannot completely answer this. It's not my expertise at all. But they want the band gaps we are moving around here seem to be nice in this regard. Maybe there's someone more expert in the audience which can help on that. Yeah, sorry about that. Like, okay.
But there's a particular target, like, are you saying that if the band gap is around 2.8 EV, then that's good for photocatalysis?
I don't know if it's just the only factor. I'm myself no expert, but
No, I don't know anything
Right.
either. That's what I'm asking. So it's
titanium
like in like
dioxide. Titanium dioxide is also in that range, around 3, I believe, depending on the phase. So yeah, there's something around there, but yeah. Okay. Question. Okay, and well, after looking a bit at the structure, we once again move to the magnetic properties, which again, in this case, you can consider a lot of different magnetic configurations. Here I show just some of them. Well, we have once again the GAFM and antiferromagnetic bilayers structure with ferromagnetic planes antiferromagnetically coupled. The FAFM, where both of the couplings are antiferromagnetic, the antiferromagnetic bilines, or even the fully ferromagnetic. But in short, what we observe is that for almost all of the transition metal ilmenines, once again, the GAFM structure is the ground state, the magnetic ground state, except from copper, which was ferromagnetic, and well, zinc, which being spin compensated, it's not magnetic.
So these are the predictions.
No, these are the values we calculated. We analyzed a whole bunch of structure and we get to this.
Okay, but I guess my question is, are they always in agreement with experiment, or do they ever have any different order? So.
Oh, sorry, well, no, I said experiment. In this case, we just have experiments for the ilmenine. Yes, it's experimentally it was in the bulk case for CTO. Sorry, I messed everything up in there.
No, but I guess, but
yeah.
Does experiment agree with these
Well,
DFT predictions?
The thing is that we still don't have these compounds. We just have the iron ilmenine two-dimensional.
The others don't exist.
Yeah, the others still are not. Have not, but not in, as far as I know, or when we did this, in a thin film in two-dimensional, which this is the whole thing we were trying to do, like setting the ground for future experiments, because we are sure that, well, not completely sure, but probably they can be, if they have done it with iron and we have cobalt also, which is interesting, probably there's a way to do the two-dimensional and it's really interesting. So yes, in this case, we just have the experimental values for iron. But well, we see that most of them have actually this ground state, which is the one we observed in bulk cobalt. Yes.
For other existing in the past.
Yes, I haven't actually brought that data here, but yes, that's actually interesting for some compounds. This is different from their bulk counterparts. I don't have the data here, but we did some fast checks. And for example, well, cobalt stays the same, but yeah, some of them actually change.
So those are 1 unit cell thick, your calculations?
Yes, these are the two-dimensional. Like this is the
but it's 2 units. It's 1 unit cell, not 2 or 3 or something like that.
One, just this. Like it could be also really interesting, but it's another work doing multi-layers and see where you recover the bulk. But that's a whole bunch of calculations, I'm afraid. Okay, this is just one thing. So well, we also here we have another way of showing the same data, where we observe that even though in most of the compounds these two configurations, the GAFM and FAFM, were had a similar trend, but below half filling, the other states were much higher energy, and we observe that above half filling, we have some odd even oscillation of these states going up and down in energy, where we again see some peak in cobalt, indicating that it might be different. So we move, about the magnetic properties. These configurations, well, can again be modeled to a simple Heisenberg Hamiltonian of one interlayer and one intralayer coupling. And well, I got both of them here. And the main takeaway here is that now, in this two-dimensional case, the J1 interlayer coupling is much larger than the intralayer coupling. you see at the order of magnitude here, or from -60 to 40 millieVs, and here you have just 1 to 2. We see that these atoms are way more coupled magnetically in the vertical direction, let's say, than they are inside the plane. So we will no longer have this case in which we can have ferromagnetic planes at larger temperatures than a nil temperature. Okay. Yeah, let's move on. Okay, well, all of this magnetism is also very related to electronic structure. Here we plot the local magnetic moment of each ilmenine regarding a filling model we did, where here we divide the electronic orbitals, the d orbitals, into 3 groups, let's say. In red we have the orbitals that are just in plane, in green is the dz squared out of plane orbital, and blue is the orbitals with both components in and out of plane. And we, after exhaustive calculations and band structures and trying to fit everything, we derived this band filling model, which also yields us the local magnetic moment. We see that it follows a Slater-Pauling-like curve. And well, I cannot go all over all of them, but this filling model can give us some insights on the spin density around the transition metals. For example, if we take, I don't know, with vanadium, we see that we have the out of plane and the out in plane orbitals, ones with both component fields, so have something with this shape. And if we go to cobalt, for example, to make a link with the previous part of the talk, we have here that cobalt has spin density both in plane, but also some out of plane component. We see here cobalt, even though the anisotropy now is turned in plane, we will talk about the anisotropy in the next slide, still has some density outside of the plane. So cobalt once again appears to be a more complex element with a tricky isotropy. So we will move now to the actual anisotropy. We did it similar to the previous case. We studied whether the compounds prefer to have the spins outside of the plane or aligned in the plane for the different ilmenines. And we find a trend, a quite nice trend, which is below half filling, the anisotropy wants to be out of the plane, and above half filling, it turns in plane actually. Some compounds like chromium have a large magnetic anisotropy, also iron and cobalt, while others have the anisotropy is smaller. Also, when we are inside of the plane, the direction, the spin oriented was one of these equivalent dashed cobalt titanium directions always. So all in all, I think this is the summary of the part. Yes, so ilmenines, even though they have similarities to the ilmenites, they have some crucial structural differences with respect to them. They have a GFM magnetic ground state, while also some of them presenting a large magnetic anisotropy, both out and in plane, depending on the compound. So for example, chromium ilmenine could be interesting for magnetic storage applications, while iron or cobalt ilmenines, for example, for magnon injection in the terahertz range. And well, the most important takeaway, I think, is that iron ilmenine has been experimentally synthesized, so the rest of ilmenines probably can be too, and it would be very nice to have experiments on these compounds. So yeah, let's look at it. Let's go for it. So just acknowledge all our funding, our collaborators, and thanks for your attention. I will be happy to answer any questions you might have. And
Great.
thank you.
Okay, so anyone online who has questions,
let's see.
please enter those into
There's
the chat.
yeah, can you there's some questions, I think.
Yeah.
Yes.
Yeah,
Well,
let's
hi.
put the
Nice
micro.
presentation. I wonder if any of those oxides are ferroelectric. you seems to have not mentioned it.
Sorry, excuse me. I think,
Electric.
good question. As far as I know, no, right. As far as I know, don't. No, they are not.
They're not.
Mhm. There's.
Other questions from online audience? I guess maybe I can ask one.
Sure, sure.
So what are the next steps here? It seems like you've done a rather complete study of these ilmenites and like
Yes.
different material compositions, looking at the 2D version.
Mhm.
So what are the next things that you're interested in looking at, and why are those things what you're most excited about?
That's a good question. Yeah, like we did a very like the basic work here. So now we think that it's the turn like for the exciting things. But it would be first of all very nice to have some experimental insight, like see that someone has synthesized, for example, CTO ilmenine, like two-dimensional version, see what happens in contrast with the bulk. Probably some experimental feedback is needed. Is there any question? I think.
No, that was just an email coming.
Okay, okay. Sorry. Yes, sure.
Well, you mentioned that the interlayer J, the J1 is much larger than J2 in the 2D.
Mm-hmm.
2D version.
Yes, yes.
What is the situation in 3D version? And if they are different, then
In 3D, it was in 3D we just studied cobalt, but it was actually the opposite. So you first lost J1, it was smaller, but J2 was very strong, so you kept ferromagnetism inside of the layers for way longer. There's okay, yeah, here it's also I forgot to mention, but it's because of how the structure changes. Because when we have, let me show you in a second. View, yeah, when you show look at the two-dimensional structure, yes, here we lose in 3D. Here we have another neighbor. So now the in-layer structure is like structurally weaker, apart from having the atoms more squashed together in the z-axis. So yeah, there's a structural change from 3D to 2D that makes now also the magnetic coupling it's opposite in some way. Like yeah, now the leading term is the interlayer. So it's a interplay between the
It will
two.
be interesting when you add more layers. What to say?
Sure.
As a single layer. If you put 2, 3, when you will recover.
Yeah, I see.
That's interesting. But in fact, we did already some preliminary tests about that. But the main problem is that we have not, let's say, it's strongly dependent on the compound. Whether it's
Sure.
cobalt or is iron is different. Then we have like a mesh of that task, but then we have to organize all of those. Okay.
Yes.
So we still already did some calculations for that.
So I guess maybe for example, after you grow a few layers, then maybe you can see a situation where it's at a critical point where J1 is roughly equal to J2.
Yes.
That's a good point. In some cases, yeah, there is going to be a transition at some point. So it would be a nice calculation probably, but it's going to be different for each compound. Like some might recover at 2 layers already recover the bulk order, but some maybe they need more layers. And it's it's very interesting actually, but it's going to take time.
You see also that all the 2D materials, these kind of things we have done, is almost in the same magnetic structure. No, it's like antiferromagnetically coupled between up and down, and is antiferromagnetic couple is ferromagnetical couple on the top. But you notice that, for instance, you do manganese, then the manganese compound, for instance, prefer to be in the layers as bulk, prefers to be antiferromagnetic couple in the layers, and then antiferromagnetic couple between layers. So it's a different, completely different structure. We have analyzed all of those, many others, but
then connecting the dots between 2D and 3D, it's a hard work.
Larger number of layers, it will be interesting situations.
Yes, yes,
So
sure.
some of them can be having even non-collinear orders. For instance, manganese with very small anisotropies that we have, or nickel, I would predict that those will be non-collinear orders. Or we have like spirals and things like that, which will be very interesting, for instance, for all these magnons stuff and things like that. But this is what I will predict from this data. But we have to do more. It's like this is recharge. We are on the flight. We are on the. We are being recharged. So there are many things we do.
So the G-type antiferromagnetism, does that assume a collinear order, or does it also permit a little bit of canting?
That I think it's
Like, I don't
outside
remember
of the
that
scope
calculation.
of the calculations we did. Like
But you're
we
collinear.
uh,
have canting
we
on
have
the-
mostly collinear. We added the spin orbit coupling, and in principle we could be having some slight canting, but we are not observing this in the calculations. Maybe if we enforced the
There is some canting because the L and the S, when you depart a little bit from being here or there,
Yeah.
L and S are not out.
Okay, maybe
there
I
is
can
some
show
non-collinearity.
something.
In fact,
Yes,
we have in
well,
the figure of the
I have it somewhere
the
around
SUV
here.
figure.
Yes,
when you
yes.
say-
In bulk, we observe this.
But when you say G-type, does the G-type mean canting or no canting, or
No.
does it not contain the information about it?
In principle, it's not saying nothing of the canting. G-type is just saying that it's ferromagnetic coupled antiferromagnetically in the z-axis. But for sure, you could have some canting. The thing is, we have not observed because, well, in this case, yes, in the bulk, yes, there's some smashing between the moves, the orbital magnetic moment and the spin magnetic moment. But also, I guess that if we were to simulate a slight canting of individual atoms in the system, that could also be a bit more stable than the collinear states we start with. But in the end, it's a compromise between how many calculations you can do, because already it's time consuming analyzing all of these compounds, doing it properly in the purely collinear case. So to start playing with canting and so, it's really interesting, totally. But yeah, maybe you have to focus on one compound and see all of the combinations.
What this means that all the models, simple models that you can use, are more complex than we normally think. Because first the spin has to have a component that is out of plane and in plane. And also then you have another compound that is the safe anisotropy, this kind of move also has to include it. And then you see that the L and the S are not aligned when you depart a little bit. So then
That's it.
it's like the model has to be very fine to describe all these kind of things. So it has to be a very detailed model with many terms. At the end, I wonder how much you will save by doing the simple model or just doing the real calculation. Because you are like finding so many terms that at the end.
I mean, it probably depends on what kind of quantitative agreement
Yes,
you're happy with.
you want to.
Yeah.
Sure.
But mostly my concern is that you lose some qualitative things because you lose this kind of canting when you go musuel, and musuels are not really aligned when you go out of the
Especially-
lines, or you have the like two. Of course, when you have this moment, it's like I have two things. You say, well, this is the bigger, this is the one that is predominant. But the other thing could play when you go to temperature effects, or you put a laser, and I have some excitations. Then these terms will play. They have to play. Yeah, because there are other terms that are not the main, the dominant, but they are secondary, but they are like almost equal in the quantity. So then when you do an excitations, for instance, with a laser, then you have to see some strange effects there.
Okay, are there any other questions from the online audience or in-person audience? Okay, if not, let's thank Mikel once more, and he's again
Thank you.
around for the rest of the week, so.